y equals 4.
Wait, you mean x equals
Y equals 4. I'm not talking about your question.
on 44?
No.
I got x equals 4.
Yeah, okay.
Yeah, that's what I got for 40.
Alright, so for 40, we are finding the equation of a line that goes through these points. So the first thing we want to do is find the slope, right? So y2 minus y1 over x2 minus x1. Right, so my y values are -7 and 3. So -7 minus 3 over my x values, 4 minus 4. So I get -10 over 0. What does that mean? What happens if I get a 0 in the denominator of my slope? It's undefined. So is that a horizontal or vertical line? Vertical. Right? So I know from this slope it's a vertical line. That means it will be in the form x equals or y equals?
X equals.
X equals. So from this information, x equals what? X equals 4, whatever the x coordinate of those points is. Right? So the equation of the line is x equals 4. You okay with that one?
Yep.
What else? 30. So on this one, we are given a point and a slope, and we want to write the equation and sketch it out. Yeah, so -1, 0, and 2, 5. All right, so on this, right, we're given a point and the slope to write the equation of the line. You probably want to use point-slope form. Okay, now this point that we're given is an x-intercept, right? It's not a y-intercept, so we couldn't just jump into slope-intercept form, right? If we're only given an x-intercept, we would have to treat that just as a regular coordinate point. So my y1 would be 0, my m is 2/5, and then my x1 is -1, so this would be x minus -1 or x plus 1. So I would end up with y equals 2/5 x plus 2/5 for the equation of my line when I distribute this 2/5 through. Then if we want to sketch that, right, they give us one coordinate point, so -1, 0. And then I could say, well, the y-intercept is 2/5, or if I want to be a little bit more precise, I could just use the slope and say, well, from this point, from -1, 0, I'm going to go up to, right, 5. Right? So up to, and then right 1, 2, 3, 4, 5 to get an exact coordinate point. So the line should look something like that. You okay with that one?
This is not what I forgot to show you the first two. You showed me 4 pages. How many pages are there? 6.
All right, what else? 6. All right, so we've got
Someone
all right, so this is our graph, and let's see, so this is dollars and this is minutes. So parts A and B just ask, well, what do the two intercepts represent, right? What's the y-intercept? What's the x-intercept? Right, so the y-intercept would be $15 and 0 minutes, right? That would be, well, I paid $15 and I haven't used any of my minutes yet. With x-intercept, you're at 75 minutes and $0. So that would be after you've used all $15, you've been able to talk for 75 minutes on this prepaid card, right? Then part C, write an equation for this graph. Right? Well, there's a couple of ways we can do it. Right? I know 2 coordinate points on the graph. Right? I know the point 0, 15, and I know the point 75, 0. So I just want to write the equation of a line that goes between those 2 points. So I need to find the slope first. Right? So y2 minus y1 over x2 minus x1. So my y's are 15 and 0. 15 minus 0 over 0 minus 75. So that would be 15 over negative 75, which would reduce to negative 1/5, right? Now in this case, we are just given the y-intercept, right? So I don't have to put this into point slope form. Okay, you can, right? But we could save ourselves a little bit of work. Just say, well, the equation is going to be negative 1/5 x plus 15. Okay, the y-intercept there. Okay, now you certainly could set it up with y minus y1 equals m times x minus x1 and use either of these coordinate points, but this is the equation that we should end up with at the end. All right? And then part D asks, well, what is the cost per minute of calling from this cell phone? Okay, so what we want to figure out is, what does this slope actually mean? Right? Negative 1/5. Well, that's saying every time I use a minute, my total amount of money left on the card is going down by 1/5 of a dollar. Right? That means that each minute would cost 20 cents. And that's what this, we're just interpreting what this negative 1/5 slope means. Right? Negative 1/5 of a dollar. Every minute costs 1/5 of a dollar, or 20 cents. You okay with that one? What else? All right. On this one, we're just finding slope between these 2 weird-looking points. So our points are 1 minus the square root of 3 is 0. And 1 plus the square root of 3, 3 times the square root of 3. Alright, so we can just label them x1, y1, x2, y2, plug them in. So y2 minus y1, right? So that'll be 3 radical 3 minus 0 over 1 plus the square root of 3 minus 1 minus the square root of 3. Right? So I'll try to simplify now. So in the numerator, we would just get 3 times the square root of 3. And in the denominator, well, 1 minus 1, that'll cancel out, right? And then I've got the square root of 3 minus negative square root of 3. So that would be like the square root of 3 plus the square root of 3. So that would end up as just 2 times the square root of 3. Right? So now we can cancel out these radicals since I'm multiplying. And we just get 3 halves. So I guess it does end up canceling out.
Mr. Patch, you're a liar.
My law.
I think that's a lie.
I just proved it to be true. You okay with that one? Right. And then I guess it does ask you to tell whether that means the line is rising, falling, horizontal, or vertical. So if we get a positive slope, it's rising. Okay. Other questions? All right. And today, we're going to talk about functions.
You're yours now, my child. All right.
Alright, I guess first, the plan for the week, okay, we're going to do, yeah, we did that last week.
Oh yeah, that's right.
Yeah. Alright,
Oh, good thing we're
alright,
done.
we did that last week.
Good thing we're already done with it.
Alright, so, we're going to do 2-4 today, 2-5 tomorrow, 2-6 on Thursday, and then we're going to do a quiz over the first part of the book that we've talked about on Friday. Generally, for a quiz, we're not going to do any sort of review, okay? It'll just be up to you to review problems that we've done for homework, review your notes, and prepare for a quiz, okay? For a test, we will do review in class together, okay? But for like a mid-chapter quiz, we're not going to take a class period to do review. Okay, so that's the plan. Right? All right. Today we're going to talk about functions. Okay, and then we'll get into things like domain and range today as well. So first, okay, a little bit broader than function. What's a relation? Does anybody remember how to define a relation? Alright, so a relation is just a mapping between two sets. Okay, a mapping between two sets. So some rule, okay, that maps one set onto another. Okay, the first set of components in a relation is called the domain. The second set is called the range. Okay, so a function then is a specific type of relation. Okay, how do we get more specific here? Define a function. Remember that? Okay, so a relation is just any mapping between or from one set onto another. But then a function kind of narrows that down a little bit. And there's a rule to define a function here. It's not just mapping one set onto another. It's mapping one set onto another where what happens.
That's oh man, that's exactly. That's what I was thinking. I was going to say it a little bit later.
Each element in the domain is mapped to exact one element in the range. In other words, okay, if we have an input, right, or an x value, that can't be mapped to multiple y values, right? We can't have some rule where if we put in a 2, we get out 7, but then if we put in 2, we get out -4 the next time, right? That's a function, right? For each input, there is exactly one output. Okay, we can't have multiple outputs for the same input. And so that's just, this is saying that kind of complicated, I guess, using specific vocabulary. Right? Each element in the domain is mapped to exactly one element in the range. Okay, so we're going to look at multiple representations of that. Right? First, a correspondence diagram. Okay, so a correspondence diagram is just kind of, you see those circles, right, with arrows mapping things, right? So something like this. Okay, these are my two sets, 1, 2, 3, and A, B, C. And I want to map the first set onto the second set, right? So let's say I map 1 to B, and I map 2 to C, and I map 3 to A, right? That's my correspondence diagram, mapping the first set onto the second set, okay? So what I drew here a function or not a function?
Yes.
Why? Because, yeah, each element in the domain is mapped to exactly one element in the range. Okay?
I mean, you didn't have to do that. You would have done it eventually, I'm sure.
How about this? Is this a function? Is each element in the domain mapped to exactly one element in the range? Seeing a lot of no's. This is a function. Right? For each input, I get exactly one output. That output can be the same thing, right? But each input gives me one output. I'm not putting in 3 and getting A, and then putting in 3 and getting C, right? For each input, I get one output. That output can be the same, right? I can put in different output or different inputs and get the same output, right? But in this last example, right, we do 1, 2, 3, A, B, C, right? And we map 1 to A, 1 to C, and 2 to B, 3 to C, right? Something like this. This one is not a function, okay? Because 1 is being mapped to 2 different values, okay? I'm inputting 1 and getting out A or getting out C, right? This is the only scenario where it is not a function, right? Where one input value is being mapped to 2 different output values. Okay? So that's from a correspondence diagram, what we're looking for to determine whether something is a function or not. Okay? From a table, what are we looking for in a table? Right, so here we're given, input-output values. Right? So it's similar to a correspondence diagram, except this is a little more mathematical. Right? So we can input 1, 2, 3 and get out 4, 5, 6. that a function? Yeah, right? Each input is getting mapped to exactly one output. About that. Is that a function? Why is that not a function? Right, 2 is being mapped to 2 different y values. Right? I input 2 one time and I get out 5, then I put in 2 and I get out 6 the next time. Right? That is not a function. How about 2? How about that? Is that a function? Even though the y value is the same every time? Yes, right? This is still a function because for each input, I'm getting exactly one output. That output can be the same as long as I'm only mapping each input to one output. Yeah, so this graph will just be horizontal line, right? Y equals 4. We okay with those two? All right, how about from a graph? How do I tell if something is a function from a graph? Use the what? The smartboard? No, because then I would have to go through and make smart notes. It's just easier to use the PDF. Also, the pen is kind of wonky. Yeah, I just like using the driver smart. And I don't have to worry about saving the notes. Recording it.
Oh, smart.
How do we tell if something is a function from a graph? I think this is usually the easiest one to remember and to use in practice. Right? Vertical line test. Right? We want to see if something passes the vertical line test. So what that means, right? If I draw a graph, I don't know. Let's start with something like this. Right? I want to see if at every point, if I draw a vertical line, that line only hits one value. Right? So if I draw a vertical line in a lot of different places here, that's going to hit once, twice. If the vertical line ever hits more than once on the graph, it is not a function. Right? This is not a function. So if we think about what that means in terms of what we just talked about, right? For each input, right? Let's say that this is an input of 1, right? Our x value is 1. We're getting out 2 different y values for that input. That means it's not a function. Okay? Or something like this. And we've got a normal parabola. Okay? This would pass the vertical line test, right? No matter where I draw a vertical line, I'm only going to hit one value on this graph. That means it passes the vertical line test. That means this is a function. Okay, now, you will also see things like this with just points drawn on the graph. Right? So you could have something like this. Right? This relation like this, and we want to know, well, does this pass the vertical line test? Is this a function? Right? Well, all we want to see then is, well, do any of these points have the same x value? Well, it appears that these 2 points do, right? If I draw a vertical line, I would hit 2 coordinate points. Therefore, this is not a function. So we want to test to see if something passes the vertical line test. Let's see whether it is a function or not. Right. You okay with that one? Now, the last way to test to see if something is a function is from an equation. Okay? So, whenever we have an equation, okay, first we want to solve for y. Okay? Sometimes that will already be done for you, sometimes it won't be. Okay? So we want to make sure that we solve for y first, and then check to see if an input value could be mapped to multiple output values. Right? So I guess it makes more sense to just look at some examples. Right? So let's say we've got x plus y equals 4. Right? Well, solve for y first. Right? So all I would need to do is subtract the x over. So y equals negative x plus 4. Now, is there any possible way that if I put in some value for x, I get out multiple y values? If I put in 4, is there any way that I would get 2 different y values? Right? Is that possible? No, right? It's not. So this would be an example of a function. How about this? X squared plus y squared equals 7. So solve for y first, right? So subtract the x squared over. And take the square root. You get y equals plus or minus the square root of 7 minus x squared. In this case, am I going to get more than one output value for each input value? Yes, right? Because of that plus or minus. Right? I'll get 2 different output values for every input value because of that plus or minus. Okay? Except for the square root of 7, because that will give me 0. Right? So in this case, this does not give me a function. What is the, do we know what the graph of this is? X squared plus y squared equals 7? What does that graph look like? I think I heard it. Circle. Yeah, it's just a circle. Right? That's a circle with a radius of the square root of 7. Right? We'll talk a lot more about circles later on in the year. Right? So you don't need to be able to recognize that that's a circle right now. Okay? But you should be able to solve for y and say, well, since there's a plus or minus there, this is not a function. And I'm going to get 2 different outputs for each input. Questions? All right. Let's flip over to the back. First thing, okay, is just using function notation. All right, so I want to make sure that we are able to understand what this means and use it. So we're given a function, f of x equals 2x squared minus 3x plus 4. So first, is that a function? So, we can think about f of x is the same thing as y, right? So it's already solved for y. So it's 2x squared minus 3x plus 4, a function. Yeah, right? That's just a parabola. Right? I don't know exactly what it looks like, but I know it's a parabola. Right? A parabola is going to be a function. This notation means I'm going to input each of these values in for x. Right? So first, f of 3 means I'm going to plug in 3 everywhere I see an x. So this would be 2 times 3 squared minus 3 times 3 plus 4. Okay. And we could use a calculator, but let's see, that would give me 18, 9, 13. So sometimes it's faster to just do it, not with a calculator. f of negative 2, same thing, right? 2 times negative 2 squared minus 3 times negative 2 plus 4. We do need to be careful with our negatives, right? Because negative 2 squared is positive 4. So positive 4 times 2 is 8. Then I end up with a double negative here as well. So 8 plus 6 is 14, plus 4 is 18. Okay, so hopefully we know how to do those first two, right? Plugging in numbers into a function. But what about the last one? F of negative x. What does that look like? What does f of negative x look like? How do I? Yeah, right? It's the same idea. I'm just going to plug negative x in everywhere I see an x. So this will be 2 times negative x squared minus 3 times negative x plus 4. And simplify. So negative x squared would just be x squared, right? So this will be 2x squared. Negative 3 times negative x would be positive 3x plus 4. You okay with something like that? All right. Finding domain from an equation then. Two things we're looking for. Okay, two things we are looking for. One, I'll write these off to the side here. We cannot have, can't have 0 in the denominator. And we also cannot have negative values under a radical. Okay, there are a few other domain restrictions that we'll look at later on in the year, but for now, these are the only two we're going to look at. Okay, a function can't have a 0 in the denominator, and it can't have negatives under a radical. Bless you. Okay, so if I'm looking at this first function, right, 3x plus 7, would either of those two things apply? Right? Are there any places where there could be a 0 in the denominator or negatives under a radical? No, right? There's no denominator and there's no radical. Okay? That means that this function will be defined everywhere. Okay? I can input every single x value and get out the y value. That's what we're saying. Right? So to write my domain using interval notation, okay, what is interval notation? What does that mean? What is it? Do we remember what interval notation is? Yeah, so like writing where our domain starts and where it ends using brackets and parentheses and that kind of stuff. We remember that kind of thing. So if we're saying the domain is everything, right? There are no restrictions. Okay, there's no place where we would have 0 in the denominator or negatives under the radical. The domain is everything, meaning we would start at negative infinity and end at positive infinity. Okay. Why did I use parentheses around the infinities? You can't touch them. Exactly. Right? The brackets means it's included. Right? Parentheses means it's not included. But there's no way to include infinity. Right? Infinity isn't a number. Infinity is just an idea saying it's going to go on forever. Right? So always parentheses around infinity and negative infinity. How about B? Would either of these two ideas apply to B? Are there any places where we could have 0 in the denominator or negatives under a radical? Yeah, so what we want to think about here is the only value that we could not input is negative 5. What we want to do then, okay, in practice, okay, this one you can see pretty easily that that value is going to be negative 5. But in practice, what this means is set the denominator equal to 0 and solve. Okay, so I'm going to go ahead and write this out. Okay? So we're saying x plus 5 can't equal 0. Okay, so I guess we're not actually setting it equal to 0, we're saying it can't equal 0. Subtract the 5 over, we're saying x cannot be negative 5. Okay, because if I plug negative 5 in, I get 0 in the denominator. That's my only domain restriction. So I'm saying I can input any other value besides negative 5. Right? How would I write my domain then? What's that going to look like? Negative infinity up to negative 5. I'm not going to include negative 5, right? Because we're saying we can. Then I'm going to use our union symbol. Pick up again at negative 5, right? So this is just kind of creating a hole in our domain, right? We're saying I'm skipping over negative 5 and then going to infinity. So I'm just not including that one value. Okay? How about the next one? Would either of those two ideas apply here? Yeah. Which one? 0 in the denominator or negatives under a radical? Yeah, right? There's no radical here. So what we want to do is take the denominator and say, well, I can't have the denominator equal to 0. I want to solve this. How do I solve a quadratic like this? You just don't. I think we do. Yeah, right? We can X factor, use the quadratic formula, solve by completing the square, right? All those strategies we have for solving a quadratic. If it can factor, it's worth checking that out because that's the easiest method. Right? So we can come off to the side here and do our little X factor. So I want to find two numbers that multiply to positive 3 that add to negative 4. Negative 3 and negative 1. Now, since my A value is just 1, those are my factors. Right? So this would factor into x minus 3, x minus 1. So solving this then, right, I would get x cannot be 3, and x cannot be 1. How would I use that to write my domain now? Now I've got two values that x cannot be. Yeah, it'll just be a little longer, right? The same idea here. We're just going to have two values that we have to skip. So I'm still starting at negative infinity. The first value that I have to skip is 3, right? 1. Does it matter what order I write them in? Yes, it does, right? We're going from negative infinity up to the smallest value that we have to skip, right? It does matter that we write these in order. So I'm going to negative infinity up to 1. I'm skipping 1. Then I'm going to go from 1 to the next value that I have to skip, which is 3. So this middle interval notation will just be from 1 to 3. Then my final piece, okay, if I'm skipping 3, will be 3 to infinity. Right? Questions on that? Alright, I think we've got time for one more. What about D here? We have 5 over the square root of x minus 8. Actually, let's do F. We'll come back to D. Let's do F. F, I've got square root of x squared plus 5x minus 14. Do either of these things apply? Right, negatives under the radical. So in practice, what that means is use an inequality, right? Take whatever's under the radical and say that has to be greater than or equal to 0. Has to be greater than or equal to 0. Alright? So, this means x squared plus 5x minus 14 has to be greater than or equal to 0. And we would solve that. Alright? We'll pick this up tomorrow. I think